from our colleagues, well, one of the main focus of the project was, of course, try to transform residual material from the agro sector into new products, or let's say products that have an equivalent coming from the fossil chemistry, but with this bio touch, with this bio origin actually. So the work I'm going to present here with Anna Maria is, of course, the work of probably 100 people. So you see some names here in the front slide, but of course it's a huge work of several partners and probably 100 people behind this name actually. So what was the tentative here is to transform the agro-waste through a biorefinery concept into new high-value products like bioenergy, so biofuels, biofertilizers, biomolecules, and biomaterials. So of course, as Anne Wernicke remembered us before, the tentative here is to have new molecules originated from biomaterial through chemical and biochemical processes, which are of course less harmful for the environment compared to their fossil counterpart. Okay, so the tentative is in any case to have a lower burden for the environment here. So in visual terms, what means here is that you take manure residual crops, all the material residual from the transformation of the feed industry, pass through something which can be a chemical transformation, a biochemical transformation, where anaerobic digestion is of course part of the concept because it is already there. So it's very important to keep in mind what is already at territorial level in our farms in this moment, and try to implement and transform these to have new products. And these new products can be, of course, you know, biofuels or volatile fatty acids, biopolymers, these kind of things, polyphenols, fillers, and whatever, biocomposites. And in the very end, keep in mind that it is not only a problem of products themselves, but it's also a problem of, for example, tools like a supporting system, decision supporting system, or other software tools that can help us as researcher or, for example, policymakers in their decision process, which is very important, is as well a result actually. So coming to the first part, which is dedicated to biofuels produced, of course, you know, methane is already there, and biogas, because anaerobic digestion is already largely applied at European level at farm scale. We work, as you will see in the next presentation related to processes, we work a lot on the modification and improvement of the anaerobic process, anaerobic digestion process, to have methane, biomethane, hydrogen, all these things that of course can be merely transforming into energy if you burn it, but of course if they can be used, for example, in the transformation of vehicles or public transportation, so let's say in the automotive sector in general, which is very, very important for European Union. Or if you want, staying always around the anaerobic digestion, another thing you can do is apply pyrolysis approach to anaerobic digestion, with allow you to have biofuels and syngas, for example, but also biochar, which is very important because, of course, you can use digestase as it is. We demonstrated also this with our colleague Peter Shields, but and it can be used as a fertilizer at land level, at farm level. But of course, sometimes you need to transport these nutrients, these stabilized carbon, for example, and of course pyrolysis is one of the solutions, because give you biochar as a result, as a product which can be used as a let's say an amendment for field. So you can work around anaerobic digestion and improve the products we already have today, and actually upgrade the level of these biofuels and this digestive nutrients content in order to improve the application of this process at European level at farm scale. So coming to another bioproducts we studied in the process. I give the hand to Anna Maria Celli, University of Bologna, who was leader of Work Package 4, and will illustrate us the main results in terms of bioproducts from the project. Anna Maria?
Okay. Can you hear me?
Yeah, good.
Perfect. Good morning to everybody. It's a pleasure to present some results obtained during the NoAW project in terms of bioplastics. NoAW aimed to answer some needs of plastic producer and consumers in terms of new feedstock different from traditional oil for the production of monomers, polymers, and composites. This feedstock needs to competition with the food. And we solve this problem. Can you go on, David? We solved this problem because we used agro-waste to obtain monomers, polymers, and composites. Specifically, agro-waste in these fields were winery residues, volatile fatty acid derived from anaerobic digestion, fruit, and vegetable waste. Moreover, we tried also to obtain polymers with the new functionalities. We tried to develop some strategies in order to decrease the cost of the bioplastics, and we had always in mind a clear vision concerning the end of life of the bio-based plastics. So I will show you some of the results we obtained. And please, David, can you go on? Okay. First of all, is the NoAW project focused on polyhydroxyalkanoate. Polyhydroxyalkanoate is a family of polymers, specifically polyesters. Very interesting because they are synthesized by bacteria, as it's possible to observe in the photo on the right. There are bacteria that accumulate white granules of polymers. This polymer can be extracted and is characterized by the fact that the polymer is 100% biosourced. Moreover, it's very interesting because the polymers have properties similar to those of thermoplastic, traditional thermoplastic. The properties can be tuned as a function of the chemical structure of the polymer accumulated inside the bacteria. Moreover, the polymers are 100% biodegradable, not only in soil and compost, but also in seawater. And for this reason, these materials are really very interesting. Moreover, we tried, as already described, we tried to develop some strategies to decrease the cost of these polymers. An example of products is in the next slide. Okay, thank you. We produced some biocomposites starting from polyhydroxyalkanoate, specifically from a copolymer constituted by polyhydroxybutyrate and valerate. And we used, for example, winery waste. These residues are wine shoots and wine pomaces. So they are residues containing lignocellulosic characteristics and are derived from wine making. The residues are thermally stable, so can be mixed to the polymers, and we can obtain a packaging that is completely bio-based, but not food sourced. The packaging does not contain micro nanoplastics, does not contain additives, and it fits perfectly with an idea of a circular bioeconomy. Similar biocomposites can be obtained from other resources. For example, inside the NoAW project, we prepare similar biocomposites using residues obtained from industrial starch extraction from sweet potatoes. And from the solid residues of this extraction, we prepare biocomposites, and we obtain good results, good properties, good adhesion between interface between good interface between polymer and fillers. So these materials are really very interesting for future applications. In the next slide, thanks. We tried also to develop plastics with new functionalities, specifically polymers suitable for active packaging. Indeed, we extract the polyphenols from wine pomace. These polyphenols can be used as additives for packaging, or also can be coated on, for example, on a tray. And in this way, we have a packaging that is 100% biosourced. Polyphenols are characterized by antibacterial and antioxidant properties. So we demonstrated that this packaging, active packaging, minimize oxidation processes in food and contribute to extend shelf life of food, for example, meat. In the figure, in the top of the slide, for example, it's possible to see the results obtained studying a chicken packed in active packaging compared with chicken packed in a blank package, not active. And it's possible to see that the total bacterial count reached the spoilage stage delayed for about 3 days in the presence of polyphenols. So it's an important result, because in this case polyphenols can extend the shelf life of meat. And other results are here described, because agro-waste can be considered also sources of other monomers in order to obtain resins and other kind of bio-based plastics. For example, inside the NoAW project, new resins free of bisphenol A have been prepared. These resins derived from tannins that were extracted, also in this case from waste, wine pomace seeds. And these resins were also obtained by using succinic acid, obtained also in the NoAW project by starting from fruit and vegetable waste. So using a 100% biosourced succinic acid. These new resins are interesting because suitable for a range of applications, for example, for coating, for paints, for adhesive, for composite materials. And in this case, it's necessary to underline that these materials are not biodegradable, but potentially recyclable. So the end of life is different in this case. Other monomers can be obtained, for example, by extraction of other molecules from agro-waste. This is an example reported in the right part of the slide. In this case, we use the vanillic acid that is present in grape pomace. Vanillic acid can be used to obtain new polyesters, specifically in this case, new copolyesters. These materials are interesting because the properties are tunable according to the composition of the copolyesters. Water vapor permeability is interesting because it's between the permeability of polyethylene and polyethylene terephthalate. The copolymers are filmable and so can be suitable for packaging applications, and also in this case they are recyclable. It's interesting to observe that these materials are aromatic polyester that, for example, can substitute other traditional materials such as, for example, polyethylene terephthalate. So, as a conclusion, in the next slide, we have obtained from agro-waste biofuels, bio-fertilizer, biomolecules such as polyphenols and biosuccinic acid, and also biomaterials, for example, biocomposites, polymers with interesting functionalities such as antioxidant and antibacterial properties, and also completely new materials. More details about the processes we develop in NoAW will be discussed in season 4. Thank you.